Hi everyone, thanks for coming. My name is Ratan Sebastian. I work at Commerce Tools in Berlin. We're an e-commerce company making APIs for people to build web shops on top of. Hiring, if you're interested, please come talk to me later. Switch over, let's start with zippers. Okay, so the reason I picked this paper, this topic to talk about is, it's a paper by Gerard Huey, wrote this about 20 years ago as a way of, it was one of these functional pearls, like a way to do things that were common and imperative programming languages at the time in functional languages. So places where we don't allow mutation, where we don't throw exceptions, where we, so having those functional values and being able to write sort of imperative programs at the same time. So let me define what I'm talking about. A zipper is a tool to traverse and mutate recursive data structures in a functional way. We'll go over each of those kind of highlighted points, right? So when I say traverse, I don't mean this kind of traversal, right? Map, FlatMap, filter, reduce. These are all traversals of recursive data structures. You go over entire structure with map, and you transform each of the values in each of the nodes. FlatMap, the same thing. Filter, you remove some of the values. Reduce, you collapse the data structure down to a single value. These are all traversals. This is not the kind of traversal that I'm going to be talking about, right? I'm going to be talking about this kind of traversal. So this is a data structure A, which has a B inside it, which has a C inside it, which has int inside it. I can traverse this data structure by using .b, .c, .d, right? Like that's traversal. I'm going along the B edge and then along the C edge and along the D edge to 1. So that's how I'm traversing to access a particular value. And I can mutate it as well by traversing it using copy constructors, right? So I can copy the value inside A to a new value of B, to a new value of C, to a new value of D, right? So this is traversal, that's mutation, right, of a data structure. This is the kind of mutation I'm talking about. So where I'm saying go this way, then this way, then this way. So that's traversal and mutation that I'm going to talk about. And let's talk about the recursive part, right? So what we saw earlier was not a recursive data structure. This one is. This is a simple const list of ints, right? So you have a head, which is an int, and a tail, which is another list, and a nil is the final empty list. So here's a list of 1, 2, 3. You can access an element by going .tail, 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 .head, right? And you can change a particular element. You can change the second element to 2 by, again, using copy constructors. But you can see immediately this is a bit redundant, right? Like you're using .tail, .tail, tail. In the non-recursive case, you didn't really have a choice. You had different paths to go down. But here, perhaps, we can abstract a little bit more. And this is where zippers come in. So it's a way of doing this kind of traversal and mutation for recursive data structures in a functional way. Because, I mean, the functional way, I think, should be obvious by now, right? We're not doing any sort of mutation here. The same way copy constructors provide ways of doing something that's mutation-like without actually doing mutation. That's what we're going to be using. That's what zippers are going to be taking advantage of. OK, so we're not going to be talking about lists. I'm going to be following the original paper fairly faithfully. So we're going to be talking about tree. The first data structure we're going to be observing zippers for is trees, and specifically these kinds of trees. I tried doing a lot of these visualizations with D3. It got messy. So now you have these hand-drawn, free-range, organic images here. And yeah, hopefully they're visible. If they're not, let me know. They're probably mistakes as well. OK, but so we have items, leaves that have values, and sections, which is just a collection of subtrees, an ordered collection of subtrees, right? So an item would be an A, a section would be the subtree A and the subtree BC. Right, I've used this notation a few times because it's easier to read out, like the list B notation, A and BC. OK, this is the kind of trees we're going to be talking about. So here's an example of this tree. You have A, B, C, D, E, and F. So the paper starts by asking, how do you refer to the position D without losing the context of the rest of the tree, right? So if I wanted to say the tree A, B, C, D, E, and F at D, right, I can't just give you the value D. I need to give you the surrounding context of how I got to D, right? So that's how I can focus on the value D. And it starts by saying, like, describe the way you go down to D, essentially, right? So in order to get to D, I first go to the subtree, which is to the right of A and BC, and to the left of F, right? So I'm focusing on the part of the tree, the middle of these two things. So I have a list of lefts and a list of rights. This is my context. My current focus is a subtree DE. And then I can go down again to D, right? So I go to the left of E and to the right of nothing, and I go down to D. So my current focus now is D, and all of the context is preserved there. You can kind of see like where the term zipper comes from, right? Because if I go in the opposite direction from this focus D up to that focus DE, up to this focus of the whole tree, kind of zipping the tree back together by reassembling the components. So let's formalize this a little bit in Scala. So a zipper is a combination of a focus and a path, right? Focus is the part of the tree you're looking at, and the path is it's also called the context, the surrounding context which you disassemble to get to that point, to that focus. Path is either the top, which means that it's the whole tree. You're focusing on the whole tree, or it's a node, which is the parts of the tree that you move to the left and you went down, and the parts of the tree you move to the right, and the parent path, essentially. So here, D is the focus. This empty list is the list of lefts. The E is the list of rights. And the parent is, again, another node where the list of lefts is A and B, C. The rights is F. And above that is just top. Is this clear? Any questions at this point? OK, cool. So now that we have the structure, some operations start becoming quite easy, right? Like the kind of operations we were seeing before. So go down, for example. From the position D, from the focus DE, we can go down to D the way that we saw before. But what's interesting, I think, here is the code for this, right? So there's a few things here. We'll go over this in a bit of detail. So it's an operation on a zipper at any particular focus. The first thing you notice is that it returns an either. So these are fallible operations. You cannot go down from a leaf node. You cannot go down from an empty section, right? So those return lefts, failures. And if it's a valid non-empty section, then we can go down to the first element in that section, right? So essentially, we take the section, we disassemble the subtrees in that section. We take the first subtree, and we make it the focus of our new zipper. And we take the rest, and we make it the list of rights of that zipper, right? So notice here there is no, these are all order one operations, right? You're not traversing any structure here. You're just taking the head of a cons list, and you're creating this new structure here. It's an order one operation, go down. Go right, similarly. So if you had the focus BC, you would move right to the focus D, and then move further right to the focus E. Notice, though, that the order on the list of lefts is inverted, right? So when you move right from BC to D, BC goes to the head of the list. So you have BCA, and then you move further right, you get DBCA. The reason for this will become clear in the implementation is that so when you want to add that new focus, right, which is what you're going to be moving towards when you move right, to the head of, when you want to add it to the, the new focus is the first thing on the list of rights, and that's going to become the current focus. And the current focus is going to become the head of the list of lefts. So if you want to add it in the right order, that is A, B, C, you would have to add it at the end of the list, and that's an order n operation, right? So we try to avoid that. It'll become a problem later on, but for this operation, it's still order one because of the fact that you're reversing this list. Okay. More traversals. Go left, kind of the same as go right, but here, fortunately, you do not have that reversal operation because adding on to the beginning of a list is fast, and so these are in the right order. Go up is where the problem of the reversal comes up, right? So when you go up from the focus D to the focus A, B, C, D, E, you need to reverse the list of lefts, right? So you need to first reverse BCA to ABC, and then append it onto the cons of D and the list of rights, which is E, whatever else after that. So the reverse, first of all, is an order n operation, and the append is also an order n operation. So overall, go up is an order n operation, right? So this is the most expensive traversal operation that we have, and it's kind of an important one. Like it's kind of, if you were just traversing down the tree, if the only use case was to traverse down a tree, then you don't really need a zipper, right? You don't need the context. You can forget about it. You're just going down and left. And go up is kind of the reason you're using a zipper, and it's an expensive operation. So we'll come back to ways to make this faster later on. Okay, but before we get to that, we can derive traversals based on these kind of atomic traversals that we've already defined. So here is a way to reify your list of traversals as a list of directions. So you have a sealed trait direction, types of which are up, down, left, right. You give it a list of directions and a zipper, and you can basically fold over that list, applying the traversals one at a time. And you can compose the traversals basically how you would compose ethers, right? If the first traversal succeeds and the second traversal succeeds, then you have a successful zipper. I've done it using pattern matching, and here I've done it using FlatMap. So this is another derived traversal that says go to the nth child. So it's a combination of two types of traversals, going down and then going right n times, right? So that gives you the nth child. I've used this helper function repeat that starts with go down of zipper and then repeats the second argument function n times. So go down once, and then if it succeeds, so .write.flatMap, go right once, and then do that n times, essentially. So that's how you derive traversals by combining these atomic kind of primitive traversals. Let's talk about mutation. So the other big reason for doing this, for using zippers, is to be able to like mutate these structures in a functional way, right? Without actually overwriting values, but by like just adding references and dereferencing things. So insert down, for example. So if your focus is a section, you should be able to insert something into that section. That's what this does. So your focus is the section BC, and you're going to insert A into that section. Your new focus becomes A, and the B and C become the rights of that focus. Again, like I'm not going to go over the code for each of these, but you can see that it's still an order 1 operation. It's just like adding a new reference and moving some references around. Yeah, so new focus becomes the one that's to be inserted, and the children of the section that you're inserting into become the list of rights. Insert left, similarly how you'd expect, but again, notice that, yeah, so inserting B to the left of C will insert it at the end of, at the beginning of the list of lefts. So again, like that, those list of lefts are inverted. Insert right, adds it to the beginning of the list of rights. Okay, so those are inserts. Deletes. Delete mostly just ends up becoming a question of what takes over the focus, because a zipper always has to have a focus. At least a successful zipper needs to have a focus. So if you're deleting the thing that's at the focus, what becomes the new focus essentially is the question you have to answer when implementing delete. The paper answers it by saying first take everything from the rights, and then take from the lefts, and then go up to the parent. So here, for example, once we delete B, C becomes the new focus. You delete C, D becomes the new focus. You delete D, A becomes the new focus. And when you delete A, an empty section is the new focus. And once you try to delete that, you get, I think, yeah, you repeat essentially. But again, this is just like one implementation of a zipper. It's just the implementation in the original paper. It is by no means like what is recommended. I will show you a few other examples of zippers where different choices have been made to satisfy different use cases. But the idea generally being that you can define things like insertion and deletion without having to mutate things and in an efficient way. Change is kind of the easiest one, right? Because you already have a direct access to the thing that you're focusing on. If you just want to change it, replace it with something else. So it's literally delegation to the copy constructor of the zipper case class, right? So you copy zipper and focus equals new focus. Right, before we move on, any questions at this point? Is this all clear to everyone? Cool. Right, so let's now talk about making go up better, right? So we said it's the most expensive operation. All the inserts, deletes, traversals were all order 1 operations except go up. How do we make this better? The answer is to basically change the tree to change the representation of the tree to make it more efficient, that you don't have to make it easier to recombine a section from the zipper representation, essentially, right? So you have these 3 components at any focus of at any point in a zipper, right? You have the list of lefts, the focus, and the right. And the reason this is expensive is because you're going to have to combine them all in order to go back to the tree, what if we just did it, right? What if we just kept the components as they were? Because like we don't really know what the point of this, like how the tree is going to be used as primarily. If it's only going to be used to like traverse, if you're only going to be using the zipper to traverse the tree and change parts of it, then it's more important to you that go up is efficient than that the tree is represented as a list. So you just change the representation of the tree. Right? They refer to this as in the paper as leaving scars while doing this traversal. But the idea is that instead of having a section that's a list of subtrees, you have a section that should be list of tree of A. Sorry about that. Yeah, that should be list of tree of A. So a scarred section would just be that should be list of tree of A as well. Yeah, so scarred section will kind of replicate your definition of the node in path, right? So instead of putting them all together into a single list, you preserve the ones that were on the left, the one that was the focus, and the ones that are on the right. So when going up, instead of putting B, C, A, D, and E together in a single list, you just keep them separate, right? So this way, when you go down, I think I have a slide for this. Yeah. So when you go down along the scar as well, right? So you, when going up, you've preserved the position from which you went up. So when you go down, you can go back down along that scar. Yes, exactly. So I mean, at this point, I think it's worth talking about kind of the use cases for which like this was originally built up, right? So the two I've found that are kind of like in production code that's widely used, file systems and tiling window managers, essentially, right? So file systems, obviously, it's like a long-lived free data structure, and that's usually the case in which you want to be using this, right? Like I said at the beginning, those kind of more declarative traversals like map, reduce, and stuff like that, that's what you want to be using most of the time. And when you want to have more imperative traversals, like literally someone entered a keystroke to go to the left, and now I have to go to the left, that's when you want a structure like this. Most of the time, you want to be doing like traverse the entire structure and do some sort of summary. Yeah, so in that case, it's fine to like change the tree structure to match this particular use case, which is traversals. So yeah. Right, so you go back down along this car instead of going to the first element like we did earlier. That's what's down there. Okay, so let's talk about some real-world applications of zippers, like the ones that you'll most likely come across in your day-to-day work is in JSON libraries, and I'm going to talk about the one in Circe, particularly. Right, so the way it's organized in Circe, at least, you have this supertype that's a cursor, that's either a H cursor, which is a successful cursor, or a failed cursor. So you remember, like all of our traversal operations had return either, right? Because they were fallible operations. Circe's cursors, zippers, include the idea of a failure within the zipper itself. So a zipper doesn't necessarily have a focus; it has an option of a focus because the zipper operation might not have succeeded. You might have gotten a failed cursor. We'll see some examples in a bit. But if it's a successful cursor, it's either an object cursor, an array cursor, or a top cursor. A top cursor means that you're focusing on the entire JSON object. An object cursor means you're in subtree that's an object, and you can like traverse further down. An array cursor, you're in an array. Those are the only two parts of the JSON. Like otherwise, it's like strings and ints and booleans. Those are the only other specifications in JSON. So those you don't need to traverse. Yeah. So this is the overview. So a cursor defines this interface where, like I said, the focus doesn't necessarily always exist, might have failed. If it's successful, though, you do have a zipper to progress with. It defines like the basic kind of generic methods that you might want to do with a zipper. With focus is essentially change, right? The function, it's change. Well, change that I showed you earlier was kind of set, right? This is instead a function to take the existing value and modify it in some way according to this function f. And this is applicable at any point that it's a successful cursor, at any point that you have a successful focus. And set. Okay, so now let's look at the interesting bits. So array cursor and object cursor, essentially. It doesn't have the same encoding as the white paper prescribes, right? So this is not a list of lefts, a focus, and a list of rights. Instead, you have an indexed collection, in this case a vector, with its index. So instead of moving things between the list of lefts, right, and the focus, you just like have an index collection in which random access and random updates, updates at random indexes are efficient, both of which properties vector provides, right? So you can say, get me the value at index 3 in the vector, and that's like an order one-ish operation, or update at the same value and the same kind of thing. So yeah, you use these existing indexed collections to implement cursors in Circe. And then you can define your basic traversal operations like left and first. So your traversal operations now become just manipulations of the index rather than manipulations of the left and right trees. So left is just index -1, first is index equals 0. They also have, since it all derives from the same type hierarchy, you can have unsupported operations on each of these cursors, like field. Field only makes sense in object cursor, but it's defined for all of them. So if you try to do field on a array cursor, you get a failed cursor. Object cursor is again an index collection, JSON object. It's basically a map from string to JSON, but the keys are sorted for reasons I'm not going to go into. But yeah, it's basically an index collection, object, and a key into that index collection, which allows you to do things like field, again, by just like manipulating. Field is basically, if your focus is an object, then you can get to a value inside that object by giving it a particular key, right? So traverse down a particular key. Okay. And top cursor is finally the entire JSON object, and the only valid operation you can do on it is to go down a particular field, because in valid JSON, top cursor is always for an object, and you always go down to a particular field. I have pictures. So given the JSON object A, 1B, and C, D, you can go down through A to the focus 1B, right? And then use the first. So from the top cursor, you've now got an object cursor where the key is A, right? So remember, like in all of this, you still have access to the original. The original object remains unchanged, right? You're just using the, well, unless you change it, but it's still a single reference, right? You're not, unlike the other zipper where you're constantly moving things around, you kind of delegated that moving around to the implementations of these vectors and map data structures. So the only interesting point here in these operations, the only thing that's going to be changing is, at least in the traversals, are the key and index values. So from the top cursor, if you go down a field, the only thing you do is set the key to A, right? And then you go to the first element in the list 1B, you set the index to 0. And when you go right, you set the index to 0 plus 1. From those basic traversals, you can derive ones like left n, which means if your current focus is an element in an array, you can move left n places, or right n is the same thing, or you can move left until this predicate evaluates to true. Delete, go left. Like you remember when we implemented delete, we picked an ad hoc way of choosing which element would take the new focus. Circe gives you more control over which element is taking the new focus. When you delete an element, you can say delete go left, or delete go right, delete go up. Delete lefts, same thing. Set lefts, where you just change all the elements to the left of where you are currently. These are, so those are like traversal and mutation operations for arrays. And there are some traversal and mutation operations, derived traversal and mutation operations for objects. So if your current focus is an object, you can go downfield using downfield, or you can delete the current focus and move to a sibling that you choose with value k. And yeah, all of these are derived from the ones that I showed you earlier. Okay, yeah, so I think we have time. We can go into, this is a paper by Conor McBride called, a really cool paper called the derivative of a data type is its one whole context. And we'll get to why in a second. So I'm going to show a very basic example of how you can apply, how you can derive zippers for any data structure, essentially. Not any data structure. There's limits on what the data structure is, but I'm going to quote it wrong, so I'm not going to mention it. That's the definition of what a regular data structure is, essentially. But let's just talk about B-trees for now and see if we can get an intuition for why this works. And then I'll just refer you to the paper for like more detail. So a B-tree is one where there's a leaf, there's no value at the leaves, and there's a value at each of the branches. There's a value A, a left B-tree, and a right B-tree. So the first thing we're going to do is remove recursion from this data structure, right? So we're going to replace every instance of every instance in the constructor of a recursive reference to the data structure with a type parameter R, essentially, right? So we're going to introduce a type parameter R in B-tree. It's called the pattern function, but let's forget about that for now. So we're going to introduce type parameter R. Leaf, nothing changes. There's no recursive reference in the definition of leaf. In the definition of branch, though, wherever we have B-tree of A, we're going to replace that with R. So now our left is just anything of type R, right is just anything of type R as well. I'm going to hand wave over this, but basically you can get back to the original structure, the B-tree structure from B-tree F. That's B-tree F, by applying fix to it. So I'm not going to get into fix, but essentially like just trust that it puts recursion back into a non-recursive structure, right? So you have this whole R that we extracted, and fix puts the recursion back. So B-tree F is a non-recursive data structure. Fix of B-tree F is back to the recursive data structure. That's good enough for now. The next thing we're going to do is try and get to a polynomial representation of this data structure, right? So everyone familiar with sum and product types, right? So you can construct most data structures by saying it's a combination of this thing and this thing and this thing, or it is this thing or this thing or this thing, right? So we're going to call those and things products, and basically use like polynomial product operations here. So you can imagine like B-tree of A and R is 1, which represents like the constant leaf, plus, which is and, or, an A and an R and an R, right? That's what branch F is. It's an A and a left and a right. So it's leaf or A and left and right. So it's 1 plus A dot R dot R. And that's basically, we're going to do some, polynomial algebra to this, right? So it's 1 plus AR square, and we're going to take the derivative of this the same way you would for any polynomial. So the derivative of 1 plus AR square is 2AR, all right? Turns out there's a relationship between this derivative and the definition of the zipper, right? So 2AR can be thought of as, or A to R can be thought of as A and 1 or 1 and R, right? So 1 or 1 is two constants. I'm going to represent it using this seal trait 2. So 2 is either left or right. And it turns out that you can define the B-tree of zipper, the zipper of B-tree as a focus and a context as just a list of A to R, right? A list of A and 2 and a B-tree of A, which is that recursive part. So again, give you a visual representation of it. So you have this B-tree of A, B, C, D, E. And what that A to R represents essentially is, in order to get to E, I need to record the value at each branch, the A bit, the direction I went in, the left bit, and the value of the tree in the direction I didn't go in, right? So I start from A and I went left to B, and I didn't take the tree C, right? And then from B, I went right, and I didn't take the tree E, and I got to E. So you can see how I'm preserving the information I need to put the tree back together by going down this way. It's weird that a relationship like this exists between derivation of polynomials and data structures, but it does, and yeah, that was very cool. All right, that's it. Any questions? Mm-hmm. 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 So in terms of like because. Oh, I see. Okay, so there's a lot of like garbage being generated. So possibly then like your like representations using vectors or some other indexed collection might be better. In that case, like you're not producing as much garbage and not as much combining and recombining. Yeah, definitely possible in that case. Yeah, there's some optimization for zipper. Like I said, because I mean some of that representation is because of its usage as a zipper. Like I think you could use a list instead if it weren't for the fact that it was zipper. Mm-hmm. Mm-hmm. Yeah. So lenses, I mean, as far as I know, is mostly for like non-recursive data structures, right? I think it is. I mean, like in the example I showed right at the beginning, like motivating this. Yeah, like the dot b dot c dot d is effectively like a lens, right? And those copy constructors are the set of the lens. So yeah, I think. I mean, I'm don't copy me, but I think that is like lenses are for non-recursive data structures, zippers for recursive ones. But I think like some of these ideas might like meld together at some point. Like it's not very distinct. Yeah. Nothing else? All right then. Thank you all for coming, and yeah.